Hi everyone, here's Ray from UC Santa Barbara. I'm going to introduce my work, Tell Me What Happened, Unifying Text-Guided Video Completion via Multimodal Masked Video Generation. This project is done when I was interning at Meta AI. Video prediction is to generate future video frames based on the given past. The past can be a partial video fragment or even a single starting frame. There can be a wide range of applications from video prediction, such as video compression, self-driving car, and virtual reality. But the video prediction is uncontrollable. There can be many different outcomes from the same past. For example, the agent can jump down, keep jumping, or even jump onto another platform according to this same starting frame. Another challenging is that not just the first frame can guide this video generation. Actually, humans have the ability to imagine and complete a video from partial frames at arbitrary time points. In this project, we consider three scenarios: prediction from the first frame, rewind by the last frame, and infilling between the head and the tail. If we can use language to describe the missing event and further control the video generation, we should enhance video completion as more easier and more flexible from partial visual guidance. To address all video completion tasks, we propose multimodal masked video generation, aka MMVG. For training, we have the full video and its related caption as the instruction. During inference, only partial frames, like the first or the last frame, and the instruction are provided to generate the entire video. MMVG is built upon vector quantization to represent a video as discrete tokens. We introduce temporal-aware VQ to have more smooth generative video modeling. To deal with the video frames that are not presented in chronological, we carry out video completion in an encoder-decoder manner, a masking strategy that masks different parts of the video as the input, and then we learn to produce the full target video. We first talk about our temporal VQ, which is built upon the standard training of vector quantization, including the reconstruction process involving the encoder, the decoder, and the codebook for quantization. However, we cannot directly apply it onto videos. It will ignore the inner temporal coherence. If we treat each frame as an independent image, it may result in an unsmooth video reconstruction. To address this issue, we try to inject the temporal relationship into the latent representation. Given two frames in the same video, humans are able to infer the order. We randomly select another frame in the same video and make the model distinguish the order between each other, like which one should be presented first. This binary classification of before-after is done over the latent token. So learning this order can facilitate an implicit temporal coherence into the latent Z, which also helps smooth video modeling. To learn a unified video completion model, we propose the masking strategy to obtain the masked video from diverse time points. We mask out most video frames with the probability and replace each fragment as a unique span tokens. For example, for a video with 5 frames, we reserve the third and the fifth frame and mask all the others. Our goal is to recover this missing part and perform video completion guided by the instruction. So we first apply our TVQ to get the discrete visual tokens. We also tokenize the instruction into word tokens. So after that, both video and language are in the same discrete space. We can adopt the multimodal encoder, which is a standard transformer, to perform cross-model fusion and extract the encoding features through the multi-layer self-attention. After encoding, the video decoder learns to produce all frames for comprising the complete video. It follows the autoregraphic decoding, which predicts the discrete visual tokens based on the encoding features and the past generated tokens. The final step is to apply TVQ again to reconstruct them back to the video frame, and we then have the complete video. So by varying these masking conditions, MMVG learns how to complete a video from partial frames at arbitrary time points with the text, which overcomes the limitation of the chronological guidance. After training, MMVG learns to perform video completion over span tokens. So during inference, we can format the input as the following, like put the span before the last frame for rewind, or put it between the head and tail for infilling. And in this way, a single trained MMVG can unify all video completion tasks without specific downstream fine-tuning for all tasks. For the experiments, we have 3 datasets. Kitchen is a natural egocentric video dataset about humans' kitchen activity. Flintstones is an animation from the animated series. And Multimodal is synthesis gaming clip, where the agent will adventure in the cloning run gaming simulator. The max length of a video is 16 frames, and the resolutions are all resized to 128 by 128. We have 2 metrics to evaluate the generated videos. FVD calculates the distance of I3D video features. Since our used video datasets are in a specific domain, we fine-tune clip and then calculate the relative visual text similarity, aka RCS, between the generated video and its instruction. So a higher RCS shows a higher language correlation. We treat the state-of-the-art video generation models, TATS, as the comparing baseline. They also adopt visual tokens and autoregressive transformer to model the video. However, it can only generate videos following the frame order, which can support video prediction but not rewind or infilling. Due to this chronological limitation, TATS needs specific training for each rewind and infilling task. In contrast, our MMVG can unify all tasks with a single trained model. We first take a look at video prediction. When without the guided text, MMVG surpass TATS like lower FVDs on all 3 datasets. This supports that learning from diverse time points will not hurt the prediction from the past. In contrast, our masking strategy can bring superior temporal coherence. But there are still too many possible outcomes from just the beginning. Hence, we can see a huge performance gap between with or without the instruction, especially on Multimodal. The instruction as guidance can make it related to the expected ground truth result. And if we follow the specific training to optimize MMVG for the prediction, we can obtain further improvements upon it. Rewind from the last allows the model to imagine what happened along with a suitable opening. The objects may not display on the last frame, which is make it more challenging to complete. Similar to prediction, language is still essential to rewind the past, where we can also find a huge performance gap between with or without text. Our Unifying MMVG, which is not specifically trained for rewind, can even outperform TATS on Kitchen and Flintstones. Again, if we following TATS design to further train MMVG, it can gain more improvements on the rewind task. For infilling, it is not just synthesis lows intermediate frames as video interpolation because the visual dynamics are usually changing too rapidly to handle well. With guidance from the head and tail, we find a noticeable improvement even without instruction, which is helpful in temporal video modeling. And we still need the language hint for more controllability of the expected missing events. It shows that completion from partial frames at different time points can still help in this infilling scenario. In summary, we introduce a new task, text-guided video completion, to control video generation from arbitrary partial frames via language command. We propose multimodal masked video generation, aka MMVG. MMVG contains temporal vector quantization for temporal-aware discrete visual tokens that can have smooth video reconstruction. And MMVG learns video completion upon the mask then fill training. where a single trained model can unify all prediction, rewind, and infilling by utilizing the span token. Through training on the large-scale video dataset, we can further perform text-guided natural video prediction for the open domain scenario. You can also visit this QR code for more qualitative examples. This is Ray from UC Santa Barbara. Thanks all for your listening.